Now to solve this problem, we have to consider set of governing equations. First is mass conservation. Please understand, this is only gas phase governing equations. We don't need liquid phase solution at all because it's steady. So mass flux which is coming out of the interface, this is liquid surface. So mass is coming out. This mass flux is rho u. So u is the x direction velocity. So this is x direction. We are talking about x direction. So rho u is the mass flux which is coming out. That is mass burning rate, you can say, per unit area. M dot double dash is a constant because steadily it burns. So m dot double dash is a constant. Now fuel conservation equation. Please understand that the fuel is coming out, oxygen from the ambient is coming out, and products are formed at the flame. Okay, so this is the interface. So x equal to 0 surface, then this is the flame, x equal to xf, and this is the boundary layer, x equal to del. So now fuel is coming here, oxygen is coming from this, and products are formed here. So in this inner zone, we will see fuel plus products. In the outer zone, we will see oxygen plus products, but not fuel in the outer zone. Similarly, no oxygen in the inner zone. Products which are formed in the flame zone can diffuse towards the inner and outer zones. So that means we need not solve for products. There are only 3 components in the reacting system: fuel, oxygen or oxidizer, and products. That's all. So if you know the values of these two or profiles of these two, this can be estimated. Why? Because Yp will be equal to 1 minus Yf plus Yo. So that can be applied. So we need 2 species conservation equations, how the fuel is conserved and how the oxygen is conserved, oxidizer is conserved. So now for the fuel, this is the convection term and this is the diffusion term and this is the source or the rate at which the fuel is burning. So minus sign comes because of the fact this is positive. So minus sign you have put because the fuel is consumed in the flame. Okay. So the fuel is convected as well as diffused from the surface towards the flame zone, and there it is consumed. Similarly, oxygen from the ambient or the outer side, outer zone comes and by convection here, convection, diffusion, and it is consumed again. The minus sign indicates it is consumed. Okay. So these are the governing equations. But when you write this F, for example, it is A exponent of minus EA by RUT into concentration of fuel power N1, concentration of oxygen power N2, something like this. So you can see this is a non-linear term. So okay, I can solve these 3 equations, no issue, because mass flux is constant. I can also take properties as constant, these properties as constant and solve it, but numerically only I can solve because these are non-linear terms. So what I will do, I have to think of something else. Okay, energy equation also is required, so that is also written here. This is rho u Cp, this is convection term. Again conduction, this is like a diffusion term, conduction term, and source. So the temperature increases, correct, beyond the ambient temperature. This is because of the heat release rate. So the rate at which the fuel burns, which is positive, I told you, and the heat of reaction, which is calorific value, that will give you the heat release rate, that is added to the energy equation, so that the temperature increases whenever the reaction is complete and the products are formed and heat is also exothermic reaction. So heat is released and that is added, so that causes the temperature increase. So now here I am considering a global reaction, one step reaction, where in mass basis 1 kg of fuel plus nu kg of oxidizer, which can be air, gives the mass is conserved 1 plus nu kg of products. These products can be CO2, H2O and inert N2, etc. No issue. But I am grouping all these as one species products. Now, please understand that here also there is a nonlinear term. In the fuel conservation, oxygen conservation and energy equation, there are nonlinear terms. So, when I want to have analytical solution or theoretical solution, I have to get rid of the nonlinear terms. So, I define a variable called B variable. Okay, now I am defining a variable called BFO, which is YF minus YO by nu. We note that here, if 1 kg of fuel is consumed, nu kg of oxidizer will be consumed, correct? So, that means at the reaction zone, if say 1 kg of fuel is consumed, nu kg of oxygen is consumed. That means if you at the reaction zone, the rate at which fuel is burning will be equal to rate at which oxygen is burning by nu, correct? So, this term will generate a, so if you go back and add these two, this equation plus this equation divided by nu, if I add, let us see the source term. The source term will be minus of W dot F plus omega dot O by nu. This will be my term. I am actually subtracting, so this will be minus. Okay. So, this is the term. So, now I know that if 1 kg of fuel is burned, nu kg of oxygen also is burned. So, this term will go to 0. So, that is what the source is eliminated. When I define a combined variable of fuel minus mass fraction of fuel minus mass fraction of oxidizer by nu, then the source term is gone. Similarly, I can define two more variables BOT. Take the oxygen conservation and the energy equation CPT plus delta HC into YO by nu. See, YO by nu is equal to YF at the flame zone. Please understand that. Okay. So, if I do this, then the term, source term for this will be omega dot triple dash F delta HC. Okay, so I am multiplying with Cp also this. So, Cp basically minus plus in the other term, this will be delta HC omega dot triple dash O by nu, but that will be minus 1 here. So, this term is 0 because you can see that here also Cp will come. So, yeah, you can see that this term basically will be 0 because of the fact that omega dot triple dash F equal to minus omega dot triple dash by nu. So, this will be 0. So, similarly BFT, where I am adding this CPT plus delta HC by YF into YF. So, whenever I can define a variable combining two variables and get rid of the nonlinear source term, then what I get is a conserved scalar. A conserved scalar is a variable which actually has, I will write this, a conserved scalar is a variable which actually has no nonlinear source term. So, if I define BFO or BOT or BFT, then the corresponding conservation equations will not have any source term because the source term cancels. Okay. Now, what is the advantage of that? If the source term cancels, then I can solve it in a theoretical way. I do not need numerical solution. So, I do this, and one more assumption what I make is, I say that the variable 1 by rho d equal to Cp by k, which is equal to, which is implying that Lewis number equal to 1. Further, the properties such as thermal conductivity, specific heat, density, d are all constant value. They are constant. So now please understand that rho d is constant, k is constant, Cp is also constant. So I can say k by Cp is constant. Okay. Now Z is defined as 1 by rho d or Cp by k. So I can write a expression for a B number or B variable as mass flux into either 1 by rho d or Cp by k into dV by dx equal to d square B by dx square, where B can be BFO or BOT or BFT, anything. Actually, we will solve 3 variables and get 3 solutions basically for this. But if I solve this equation with boundary conditions, I can solve other 2 variables. You can put B as BFO or BOT or BFT and solve these 3. So, I will first solve for BFO, BOT and BFT, then get back YO, YF and T. That is the thing. So, this equation does not have source term. So, I put this equation here. So, this can be solved. So, now first integrate this first for once and get one constant of integration. I will get this equation. So, this equation, separate the variables and again integrate. I will get second constant of integration. So, I will get another equation like this. So, here there are 2 constants. So, this is my solution for B in terms of x. Note that m dot double dash are constants and z's are constant. Okay. So, C1, C2 are a constant of integration. So, these are all done. So, I got B as a function of x, done. Now, in order to evaluate C1 and C2, I need 2 boundary conditions. One boundary condition, so now you have to understand, this is the interface, this is the flame and this is the boundary layer. So, now inner zone, when you go to inner zone and find solution for B, there are 2 boundary conditions. At x equal to 0, B equal to B surface. At x equal to flame, B equal to whatever be the value of B at this. So, now this BF or BS will depend upon what is the variable, whether it is BFO or BOT or BFT. Based upon these 3 variables, I will get the value of BS and BF. Okay. So, now substitute this. I will say BF and BS and substitute this and get the solution for the inner zone. Because I am concentrating on the inner zone, 2 boundary conditions are required to solve because 2 constants are appearing. So, when I solve this, I get this equation. Now, I have to just plug in the values of BS and BF etc. to get the profile. Okay. Now, go to the outer region. Outer region is flame. This is x equal to 0 interface and this is the x equal to del. Now, in this region, I am now concentrating. At the flame, B equal to BF already seen, but at x equal to del, we are in the far field. So, B equal to B infinity. So, now the solution can be got. First, you invoke one condition, then second condition, then the solution is got like this. Again, in terms of B infinity, BF and B as a function of x is got in the solution, outer region. So, we have got solution for inner region as well as the outer region, but only thing is this B now can be BFO, BOT, BFT. Similarly, corresponding to each, I will get the value of BS, BF, B infinity. For each of this, I will get this set of these values. I have to get, then I plug in and get the profiles. Okay. So, this is okay. I will list the boundary conditions later, but this is solution is got. How I got a solution? By introducing a conserved scalar. This conserved scalar does not have any nonlinear source term. Okay, now let us first talk about the boundary conditions for the real variables. There are 3 variables YF, YO and T. So, once I solve YF and YO, I can get YF, YP. Okay. So, YP equal to 1 minus YF plus YO. So, if I solve these 3, I will get temperature profile and species profiles, because here mass burning rate is constant. Similarly, the variables are also constant, the properties. That's it. So now boundary conditions, there are three locations: surface, flame and boundary layer. So now YF, take YF at the surface will have a value of YFS. This depends on surface temperature Ts. Done. Correct. Then mass flux. What is the mass flux coming out of the surface? Rho F Vf or Uf. U is the velocity in the, this is the mass flux. So that is convected. This is again rho F Uf. Convected as well as diffused towards the gas phase. So diffusion depends on the concentration or the mass fraction gradient at the surface. These are the two boundary conditions I have. But there is the zero value for YF at the flame zone because it is consumed. The fuel is consumed in the flame. Similarly, since the fuel is consumed in the flame, it will not go to the outer zone. So the outer zone between flame and the boundary layer, there will be no fuel. Take oxidizer. Oxidizer, let us come from the other direction. Oxidizer comes from the ambient. So the mass fraction of oxidizer will be equal to the concentration of the oxidizer, mass fraction of oxidizer. This is 0.23 for normal air. And this asymptotically goes when the oxidizer comes. This is flame and this is oxidizer side, say air side, and this is the fuel side. The air, actually the oxygen comes like this and consumes at this. So it goes to zero at this. So now it asymptotically goes. So I can say that the gradient of the oxygen mass fraction at x equal to 0 will be 0. It asymptotically goes, correct. But in the flame zone again oxygen is consumed, so there is nothing there. Since oxygen is consumed in the flame zone, it cannot enter the fuel zone, so that is also 0. Now go to the temperature. Temperature at the surface x equal to 0 will be surface temperature, and there is a coupling between Ts and YFS. Okay, that is due to Clashes-Clapeyron equation, thermodynamic equilibrium. You can use Clashes-Clapeyron equation, Wagner's equation, etc. Similarly, this is a steady burning case. So steady burning, what happens? The heat which is coming from the gas phase, this is Q gas to the interface, heat coming from the gas phase, the flux basically, will be equal to the mass flux into latent heat. The heat coming from the gas phase to the interface is supplied for latent heat due to steady burning. There is no liquid phase heating at all because already the temperature has reached the equilibrium temperature. This is the thermodynamic equilibrium temperature. So that means Ts and YFS is almost constant now, and whatever heat comes in is supplied for latent heat. Similarly, whatever mass comes out is transported to the gas phase by both convection as well as diffusion. That's it. Now coming to the flame surface, x equal to xf. Temperature reaches the maximum, flame temperature. Similarly, there is a flame. Here there is a flame and there is a liquid surface and there is a boundary layer. So now what happens? The inner zone, the temperature gradient in the inner zone basically here, and this is outer zone. There is a source also, mass flux into delta Hc. The flux going, the heat which is released here goes both to the inner zone as well as outer zone. The flame is trying to heat both the inner zone and the outer zone. So let us plot like this. So this is the flame and this is the fuel zone, say fuel surface, fuel, and this is the boundary layer. So now I can plot like this. The flame reaches maximum value here and actually goes like this. similarly goes like this. So, you can see that there is a flux which is generating this, reaches the maximum value and the flame temperature decreases both directions in the inner and outer zone. So, that is the balance here. Now, in the at the, so here this is the fuel side, this is oxidizer side, oxidizer. So, here it asymptotically goes to the T infinity value. So, in the outer zone I can say T will be equal to T infinity, but it asymptotically goes. So, the gradient at x equal to L will be equal to 0. So, that is the temperature profile. So, these are all the boundary conditions for the primitive variables YF, YO and T. Now, I need boundary conditions for the B variables, the conserved scalar variables BFO, BFT and BOT. Just use the boundary conditions. So, what is definition of BFO? Now, please understand that in the BFO we have defined as YF minus YO by nu, but I want to normalize this. So, what I did, this variable I have just divided by a constant value YFS minus 1, that is it. But you understand that since in the steady burning TS and YFS are almost constant, they are not going to vary anymore. So, I can say YF minus 1 is a constant. So, I am just normalizing this by this value. Similarly, at the interface boundary condition basically will be when you this is a variable I am defining, then YFS by YFS minus 1, that is it, because this I am dividing. At the flame it is 0. Now, since oxygen also is present in BFO, in the far field the oxygen at the flame again oxygen also is consumed. So, YF, YO both are 0. So, BFO will have a value of 0 in the flame zone, but in the case of the far field YF will not be there, but YO will be there. So, minus YO by nu by YFS minus 1, that will be the variable. Similarly, for all other you can check this. So, BFT is defined as actually CPT plus delta HC into YF, but I am normalizing this by HFG plus delta HC into YF minus 1, all are constant. Please see that HFG is the HFG value at T boil. So, this is also constant. Delta HC is a calorific value, that is also constant. So, this is a constant value, I am dividing it to normalize. See, I can also have the variable without dividing this by these variables, okay, not required. But why I am dividing this? Because of the fact that I am trying to make the variables vary within a small range, not in a big range, because temperature will be having very high value. So, I am dividing it by some larger value to curtail that. That is the same thing. Similarly, here also BOT, which is simply defined as CPT plus delta H into YO by nu, I am dividing by HFG to make the value normalized. So, these are all for normalization. So, once you know this value, corresponding boundary conditions from the previous slide you can apply for this. So, when you say T, whatever be the boundary conditions for, here, whatever be the boundary condition for T, you apply there. When you see YF, whatever be the boundary conditions for YF, you apply, so that you will get these boundary conditions for the B variables. So, the boundary conditions for the BFT at x equal to 0 is this, at x equal to f is this, because there is no YF at x, but TF is there. So, that will be there. Similarly, at the x equal to del, Cp infinity, T infinity will come. Similarly, for BOT, I get at the surface temperature will be there, but YO will not be there. At the flame temperature is there, but not YO. But at the ambient condition, I get this. So, basically, CPT infinity plus YO infinity by nu into delta HC will come for the ambient. So, the boundary conditions which are physical primitive variable boundary conditions in this is now transferred as the boundary conditions for the B numbers, but note that the B numbers are now normalized B numbers, because I want to B variables, I will say B variables, because these are all basically what? These are all numbers which are conserved scalars. Variables are conserved scalars. So, I get this. So, now from this, if I solve BFO, BFT and BOT, from the solution I already have got, I plug in these boundary conditions and get the values. Then what I will do? I can get the values of the TF, M dot double dash and XF. How? These are the solutions. So, after solving that B numbers, I will now solve for the mass burning rate by divided by the unit area, which is nothing but 1 by Z del. Del is the boundary layer thickness, which can be got as a function of del can be got as a function of y or Reynolds number. It is a function of Reynolds number. Okay. So, now here please understand that the B number is now defined like this. We can have couple more definitions also, but this definition works very well. Okay. So, now you can see that this B number for the mass transfer problem, no combustion, BQ you may recall was written as Cp into T infinity minus Ts divided by HFG. Now, when combustion occurs, there is a heat release rate. So, this extra term YO infinity into delta Sc by nu by del HFG also comes into added with the B number here. So, now once you know the mass loss rate, which is exactly the same expression. So, what is Z? Z is 1 by rho d and this del is like L. So, you can see that it is rho d by L into ln of 1 plus B, something like this, correct? Or we can say it is Cp by K, 1 by Z is Cp by K. So, this is equal to K by Cp L into ln of 1 plus B. So, these are the solutions which are already got, but only thing is there is a change in the expression for B in the combustion environment, which is first term added with another term which is representing the heat release rate. Now, once I got the mass loss rate, I can also get the temperature profile. Temperature profile will give you the flame temperature TF, flame temperature, which is the surface temperature plus this value. Similarly, the flame standoff, where the flame location is there, with respect to the boundary layer thickness, I can find the value of this. Okay, and mass fraction of the interface also can be found, because Ts is constant, YFS also will be found. So, in general, when there is a steady burning of a liquid pool, we can easily see that the theoretical solution can be applied by considering variables, B variables or any other variables which are conserved scalars. These conserved scalars, the advantage is we will try to eliminate the source term. The source term which are non-linear, if they are eliminated, then in one dimensional context I can get a theoretical solution. Okay, because the Gaussian equations are ordinary Gaussian equations and I can just integrate them, get constant, apply boundary conditions to get rid of the constants and get the values. Okay, so this is the end of the module 4.